A really long time ago in the 1600s, Jacob Bernoulli was studying, as we all do. He found calculating compound interest to be his passion. So he thought, let's start off with $1. He goes straight to a bank, and the bank says, your money will be compounded annually by 100%. So over the course of 1 year, he waits 1 year, goes back to the bank, and now he has $2. Now he thought, okay, well, what if the bank said money is going to be compounded every half year, so 6 months, by 50%? And again, this is still over the course of 1 year. So he waits a year, comes back, and he has $2.25. Whoa, that's 25 cents better than compounding annually by 100%. So if we started compounding more frequently, does that give us more money? If we start off with $1, we go over the course of, again, 1 year, and we decide to compound every single day. So this is going to be 1 plus 1 over 365. How much will this be? Okay, so let's plug this into our compound interest calculating formula. You have some ending value A that you end up with, and this is equal to your starting amount, $1, times your rate plus 1. 1 plus 1 over 365 to the power of how many times you're compounding it. So 365. And if we plug this into a calculator, and I get somewhere around 2.71. Okay, well that's much better than $2.25 and $2. That's about 71 cents more than $2, and about 50-ish cents more than $2.25. So what's better than compounding daily? Well, say we compound every second, or every nanosecond, or hey, even better, let's compound every instant. How do we compound every instant? Well, it's only if the time interval is extremely small, almost as if it's like 1 over infinity. Hey, that's a good idea. Okay, cool. So our initial equation is our ending value, A, is equal to P, the money we have, times 1 plus 1 over n to the power of n. The n is our rate, and then the power n is the number of times we're compounding it. Now if n approaches infinity, and p remained 1, we could just add the limit when n approaches infinity, and we saw that when n was equal to 365, when we compounded daily, our output was around 2.71. Now if we compounded every second, or every nanosecond, or every microsecond, or every instant, Euler figured out that the number would actually be 2.718281828459045, or more commonly known as E, which is what we were talking about in the beginning of the video, Euler's constant. Now this one constant, E, has so many amazing things about itself. First of all, if you raise e to the power of x and you find the derivative of that, derivative of e to the power x, this actually just becomes itself. And from this, we get the formula, derivative of any number a to the power x is equal to a to the power x times the natural log of a. And the natural log is just log base e of a. And you can see that our e, the base of the logarithm, Euler's constant, is being applied here. And our natural logarithms are applied everywhere in calculus, algebra, everything. Now, many people say that it was actually Jacob Bernoulli who discovered e, but he didn't really. He was really close. Figured out that the value we're looking for is in between 2 and 3. So e is in between 2 and 3. And it is. It's 2.71 blah blah blah. Now, Euler is the one that continued this and found out the exact value to, I think, about 18 digits, and he probably left it there.